All right. Very happy to introduce our next speaker, Gruenbohm from Ruhr-University Bochum in Germany, who will tell us a little bit about multi-step polarization switching.
Yeah, thank you very much for the introduction, and sorry for the umlaut. It's always a nightmare, but it's Gruenbohm, so a strange name. It's really great to be back here live at this conference. And although I said at the end I want to do the orthorhombic domain walls, I couldn't hold on and just give you a little bit of a glimpse on what we in general did since the last conference in my group scale bridging simulation on ferroelectric composites. So let's just start. Okay, so what are we doing? So in the group, our main goal is to contribute to the optimization of the functional properties in ferroelectric materials, like for example, for energy harvesting or caloric cooling. So to have large and reversible responses, control losses and functional fatigue, and these properties in best case for sustainable materials. So we address the material on the different scales, starting from the choice of the element, for example, in a perovskite structure, up to interface densities and morphology. But the main focus at the moment is here on the range of inhomogeneities, defects, and domain walls. And to contribute to this quest, what we do is simulations. So we want to have a predictive model because we want to really contribute and make predictions for our experimental colleagues how to optimize the materials. Therefore, we start with density functional theory because then we can address electronic structure bonding and have a good access to the energies of different structures. But I mean, what we want to have at the end is microstructure. We want to have finite temperatures and finite times, so we cannot stop at DFT. What we instead do is we use it to parameterize models on different scales. So first of all, going to the atomistic scale, we use, for example, the atomistic core shell potentials from literature, where we just have the simple interaction potential and a shell mimicking the polarizability of the atoms. This is one approach. I will show results from this today, but coming soon, we have a collaboration with a group of Ralph Droughts at our institute working on new machine learning potentials in his flavor of atomic cluster expansion. And here you just see very preliminary results. So it's just MD in a small supercell and just the first test. And you see we already got a rather good agreement of the full phase diagram of the barium titanate. So hopefully there's coming more soon. But nevertheless, one problem will definitely remain. If we have all atomic degrees of freedom, it's really, really expensive to go to large scale microstructures. And therefore, what we always also take into account or look at is at the microstructure on this coarse-grained description. So in this effective Hamiltonian, originally by Zong, Vanderbilt, and Ray. And here we use the code by Takeshi Nishimatsu. And in addition to the parametrization for pure BTO, only working based on the local dipole moment, on the local strain, we also implemented a very, let's say, simple model for solid solutions where we just have a pressure correction to deal with different ionic radii in this barium strontium titanate solid solution, for example. And here you can see that this, although simple approximation for the solid solution already gives us a good access to the whole phase diagram of the material. Furthermore, I mean, you've seen so many talks at this conference already by Ina Ponarever of the group by Laurent Village. This method is really like reliable. It has a high predictive power for phase diagrams, polarization, and domains. One warning for today's discussion here, if we speak about ferroelectric switching, the coercive field we get out of this simulations for our idealist material are larger than what you would expect in experiments, but qualitatively the trends are really reliable. Okay, so now having explained our toolbox a bit, let's motivate. So why this ferroelectric switching and why did we finally end up at this orthorhombic phase? So the starting point of this was a review article on the 100th birthday of ferroelectrics, doing something on this like more boring part of switching in standard barium titanate. And then I think it's not true that it is a boring old story. There's so many things which need to be revisited, like this switching not being homogeneous, but having more complex paths. And now also the microscopic modeling with all this different method allows us to really get a good understanding of all these processes. And then we looked on these processes in more detail. looking on the thermal stability of domain walls, looking then on the movement of domain walls in an external field and how one can accelerate or pin. First of all, in the tetraangular phase, because this is the most simple, I'd say, phase and the good model system to understand the general trends. And then finally, I will then come to the orthorhombic phase. So this is the model we use. We have a large supercell with 96 unit cells and periodic boundary conditions in this effective Hamiltonian approach. And you just have half of the system being polarized along one direction, half of the system along the other direction, and a 180-degree domain wall in the middle. If we apply a field, we would expect that the parallel domain wall here, the red one, is stabilized for sure, but we have a finite energy barrier because shifting the domain wall means that we have to shift the domain wall here from the favorable barium oxygen centered plane to the titanium oxygen plane. So this in principle means we would have one plane with zero polarization, which induces some energy penalty. So therefore we have some pin centers for our domain wall, and we have to apply a field above some activation field. Here for the simulation setup, it was 50 kilobit per centimeter. And if we do so, domain will move. So far, maybe what one would have expected. But if you have a closer look here on the profile of the polarization, you see this is the initial one. And then in the field, the domain wall gets a little bit broader. And you see that this shifting is not having the same distances. So what is happening here? So first of all, after we applied the field, after some time, the system reaches a stationary state, and we have indeed a constant velocity, which depends only on the field strength, as one would expect. But initially, we have a considerable boost. So there's a large acceleration of the domain wall just after we applied the field. And particularly my former postdoc Gruenbohm worked a lot on this and wondered what is happening. And we come up with the following model. So if we apply the field here really fast in our simulation, this field drives the dipoles in this negative anti-parallel domain out of equilibrium. So this means many of these local dipoles everywhere in the domain just switch. So if the domain wall is now reaching such a plane, we have many of these local nucleation centers already present. Yeah. So, and if we once have the nucleation centers, the rest of the process to just grow here this regions and switch the whole plane is a really fast process. So therefore, initially, we have this nucleation centers and the fast switching, but this is not stable forever because having all these local dipoles within the domain induces depolarization field and this high in energy. Therefore, with time, they quickly relax back to the steady state. And then, if we now again look at the interface of the same polarization, here in front of the domain wall, you see it's no longer many small nucleation centers. We only have a few, and then it takes much longer until the whole plane has switched. Okay, so this was the story about this initial acceleration, but we also wanted to look on the opposite. Okay, what may maybe hinder the motion, or how can we modify these? And therefore, we looked on two different kinds of inhomogeneities in our system. First of all, on strontium-rich inclusions, and second, on defect dipoles in the system. So again, we would expect if we shift the domain wall, there's a certain energy barrier, and then that these defects or inhomogeneities somehow modify this energy barrier. Here, Ari and our collaboration partner, Pierre Hirel from Lille, did a natural-elastic bands on the DFT level and on the atomistic level with Korschel potentials, showing the equal trends. And what you can see is for sure you have this energy barrier to shift the domain wall. And in the vicinity of the strontium-rich layers, this barrier is going up. Okay, one may expect that and say, oh, yeah, strontium is ferroelectric, so it should pin somehow the domain wall. But this is actually not what is happening here, because we have only very small inclusions in the system. And then if we have these, the strontium layers here are actually strained to the lattice constant of the barium titanate. So they're even more ferroelectric, so larger polarization there. And this results in this larger energy barrier. And we have the same trend not only for the paraelectric material, but as soon as we have more than about 50% or more than 60% strontium in our plane, we have this modification, and therefore one can targetedly use the concentration of the strontium to have regions with large mobility of the domain wall and reduced mobilities. One can do in principle, sorry, this I forgot. And we also then verified it with molecular dynamic simulations. And you can see here on the right-hand side, no inclusion, fast motion with this nucleation and growth mechanism on the wall. But if this wall hits the inclusion, it stops because you have a larger energy barrier to flip local dipoles. The nucleation has a higher energy barrier. And then as a second step, we then looked at the defect dipoles. But in contrast to what you may have seen yesterday at the poster, we didn't look on the real dynamics of this defect, but we just assumed, okay, there are defect dipoles in the material. We know that their dynamics is much slower. Let's just, for simplicity, keep them completely fixed. And if we do so, we had the following picture. So we assumed, again, the same domain structure with up and down dipoles. And in each of the domain, we have about 1% of defects aligned parallel up or down with the polarization. And for comparison here again, the 0% defects, you have this initial acceleration and then saturation at the rather high velocity. But if you now bring in these defect dipoles, they remove this non-equilibrium effect. So they tune the energy landscape. They reduce the domain wall velocity. And for 2% of defect dipoles, it's already perfect pinning. So the domain wall for this field strength doesn't move any longer. Okay. That's on the pinning. Now, finally, let's come to the orthorhombic domain wall. So in principle, we have the same. We have a domain wall here, a 180-degree domain wall, but now we have two components of polarization. Yeah, it's along O11 and O-1 in this case. So initially, we assumed equidistant domain walls, so no polarization here at the beginning. Then we applied the field, and you see that there's a linear increase of the polarization after some equilibration. So we have some fixed velocity in the steady state. Whereas we have again this initial acceleration with the same mechanism discussed as for the tetragonal phase. And then we had a master student, Yijing Yang, who looked on this in more detail. And just for fun, I asked her, maybe can you also look on the different components of the polarization? And then suddenly the following appeared. So while without the field, we have a clear Ising wall. If we apply the field parallel to this polarization component here, suddenly there is a block-like component on the wall appearing. So this was puzzling us. So why should this happen, that suddenly there's a perpendicular component of the polarization on the wall? And to understand that, let's look on the domain wall interface. But before we do so, I have to apologize for some kind of brain gym. For historical reason, we somehow changed the color encoding. So blue means now black and red means red. I hope you can still manage that at this time of the day. But okay, let's look on this interface. So we have the initial, the black direction now, and we have the final one parallel to the field, the red one. So these are the two possible states. And for sure, orthorhombic phase would also have these two other local minima with equal energy without any field. So why the hell do these domain walls, this polarization on the domain walls go here to this or that one? And then we looked into literature for polycrystalline materials. This has been actually predicted that it is lower in energy to not directly switch, but to switch by successive 90-degree steps. And this is what we actually see. For some reason, the resolution is a bit bad on this computer, but no worries, I hope you can still see. So what we see that we have the formation of clusters on the wall with this 90-degree switching. It's a statistical process, and either we have the blue or the pink one, doesn't matter, with the same probability. And if they meet, we have the perfect switching. So what we see is really this 90-degree switching on the wall and the successive switching. And in this intermediate state, we not only have this block-like component, we have also one-dimensional orthorhombic 90-degree domain walls on the wall and vortices, just for geometrical reasons. And to understand the microscopic mechanism behind, let's look here on this representation where we have the polarization component, the Y and Z. At the initial state, all dipoles are in this local energy minimum, and by thermal excitation, they just can leave it a little bit. And if you now apply the field, you would expect them to go to this final state, but it's the probability to not do that, but just flip only one component and go to this block-like state is much, much larger, because the energy barrier to flip here via the ferroelectric state is rather high, whereas the energy barrier to just go through an intermediate terminal phase is smaller. So locally, the polarization on the domain wall switches by 90 degrees, forms these clusters, and then with time, they just do the full switching. And this is possible not for all domain walls, but particularly for this one, because only here, having this 90-degree switching is charge neutral, elastically compatible, and this formed domain walls are really low in energy. So for tetragonal 180-degree domain wall, this would not be possible because you would have large elastic energies. Okay. Final slide, I will really hurry here. One thing I so far hide away is in the case of the orthorhombic domain walls, you can also have a high field regime that in this case, the domain walls movement of domain walls is not so relevant, but the system switches very quickly in the middle of the domain. And again, this is a multi-step procedure. And again, it's happening on a local level. But what we now have is that in the center of the domain, the dipoles are kind of rotated in the polarization space to a monoclinic phase, then to tetragonal 90-degree domain walls, orthorhombic domain walls, and they were very quickly crossing this high energy barrier for this process and switch to the final state. And with this, I hope I could convince you that it is really still a good idea to look on this switching probability processes in the standard ferroelectric materials to understand the microscopic processes. And I thank you for your attention.
Thank you for the talk. I have one question. Actually, you seem to have found in your work that once you have details, they will be domain. And that's something that I think is rather confusing. But at the same time, did you see in your situation that those details would serve as inflation sites for the users? Because sometimes people really doesn't know how to get to this inflation sites. We've seen that inflation.
So for this simulation I showed you here today, not, because there we didn't look on, we always had the domain wall already prepared and then cycling it back and forth and then kind of boring. I also would expect that there is a higher probability to nucleate a domain wall, but so far we haven't looked on this property. Mm-hmm.
I'm very interested in the defect work as well. Did you deal with it at the atomistic level? Did you set up in polarization? Because we're finding that different defect items in with different strengths, and I'm just curious how you're going to do it.
Yeah, so we're addressing it from different levels. So first of all, we just do like a parameter kinds of study, just assuming reasonable values of this and just check how they modify. And on the other hand, we have this atomistic approach to really study with DFT and DFT-MD. Okay, what is now really the defect dipole and how stable it is? And then hopefully soon it will converge.
I think really neat.
Yeah.
We don't have one.
Yeah.
Thank our speaker one more time.